Okay, so it's gone. In the last lecture, we looked at two-dimensional Fourier transforms of some images, in particular zebra images, and we saw that there was a very clear relationship between the nature of features, and in that case I focused on the wave fronts versus the point at which in frequency space where you actually got dots in your frequency space. And we had the scaling issue that the low frequencies, in other words the large features, were clustered near the center of the Fourier transform, and high frequency bits were clustered towards the edges after you'd done an FFT shift. So what we're going to do now, and what Professor Venter is going to do with you later on, is various ways of improving pictures. Okay, it's somewhat subjective, but there is a science behind even the subjectivity. And the part that I just want to introduce today is what we call frequency domain filtering. It's where you actually mess with a frequency space and then you try and get an image that improves on the original one that you have. And so the basic feature that all these things or all these techniques have is that you have an input image, f of x and y, and let's just have it our image of the iris. What you do then is you do the frequent Fourier, and typically we're just going to look at grayscales today, or at least this projector's attempted grayscales. And what we then do is we go to the frequency space. In other words, we do the Fourier transform. We take we do the discrete Fourier transform in both Python and MATLAB. What you're going to be doing is something in front but dot FFT2 of f of xy. Okay, so you're going to get a matrix of values of the intensities on your image, which is f of xy, and then you're going to apply the discrete Fourier transform to get a new image f of uv. And as we saw the last time also, all the low frequency content is here in the corners. Okay, and just to get it to us, get it in a way that we view it more naturally, in other words, an image where the origin is at the center. Okay, what we do is we then transform this thing using the periodicity of the discrete Fourier transform. We basically move this block down there, that block down there, this block up there, that block up there. And then we have a transform that is centered in the center of our image. And in order for us to see it, I've basically taken this thing, done the shift FFT, and then zoomed it up 10 times. Okay, so this is what we get then. So we now have our full representation of our image in frequency space. We've put it in a way that we can actually recognize what the features are, and now we want to do something to it. Okay, and well, one thing we can do is we basically can choose any filter. So there's something we do to it is all hidden in this filter function. So we're going to have a function huv that has the same size as fuv, in other words your image, and we have the freedom to choose it to be whatever we want. And so what we're going to do today is at least examine some of the least, the simplest choices. Okay, so for example, let us choose an HUV that looks like this. It's an ellipse, it's zoomed also 10 times, so all these subsequent images that are going to appear here is basically zoomed in 10 times because that's where all the action is. It's an ellipse that literally has zeros over here where it's white, ones over here where it's white, and zeros over here where it's black. Okay, and so what we're going to do with this thing is we're going to multiply this image with it. Okay, and remember the way I've chosen the colors for this transform, basically zeros are white and numbers are black, whereas this one is zeros are black and numbers are white. So what happens when I multiply this transform is I basically set to 0 everything inside this little ellipse and I leave everything else. So I've literally got a new Fourier transform with everything inside here zeroed. Okay, and now what I do is I'm going to say, okay, fine, this represents my new image, and I'm going to go all the way back and try and reconstruct the image from it. And I'm just going to go through the steps you've got to do. Important, you must multiply the complex transform with this filter, not the absolute value. What I've imaged here is the absolute value of the product of the two. But the thing you actually need to take the inverse transform of is actually the complex FUV multiplied by the real HUV. Okay, so the first step is to use the algorithms in MATLAB and Python. I've got to reverse the centering step. In other words, I've got to take this thing with a hole cut into it back to this Fourier transform that I can take the inverse Fourier transform of. And so there's a function that just says I shift FFT, which in essence is exactly the same as the shift FFT function. It literally takes this thing, moves it down there, takes that one, moves it up there. And if you look really, really carefully, now it's zoomed out again, you'll see that there are the zeroed sections are over there. Okay, so I first reverse the process with shift FFT. Then what I do is I compute the inverse discrete Fourier transform of number 6 using IFFT2. Okay. Then I get an image, but the problem is because I've multiplied it with a real function, there is no guarantee that this image is real. Okay, so the next step is I must go and I must convert all of 7's results to real values, and that to make the image, and I just use the absolute value of that. So I actually take the absolute value of the result in 7, and that's important, otherwise your computer program just completely throws it out when you start plotting it. And once I've taken the absolute values of it, to display the image, typically with the image it sets a certain value to white or black, and say the minimum value it sets to say white, and in this case, and the maximum value it sets to black. But it expects those minimum and maximum values to be at certain points. So what I have to do then is rescale this image. In other words, subtract off the minimum value and then divide by the difference between the maximum and the minimum value, so that all the values of the image lies between 0 and 1. Okay, before I start displaying it. Okay, and if I do those 9 steps, what do you think I'm going to get? Okay, well, the first thing is, let's just get into a place. So here's our original image blown up. Okay, and what I've basically done is, once I go through all the steps, this is the image I get. Okay, and now you can wonder whether it's an improvement or not, but there's some things to notice. Some features come out more clearly. Okay, so for that particular transformation, the one thing that you can notice is over here, all this dark stuff over here is gone. You can actually see the veins more clearly over here. Some of the dark stuff over there is gone as well. Here, in some sense, the contrast has improved as well. And over there, whereas the stuff at the back over here is a bit more blurry. Okay, so just a reminder, what we did is the filter we used was literally cutting out all the low frequency parts. So what we expected to happen is that anything that varies like really, really slowly, like this is a sine wave, or like a sine wave of n equals to 2, right? You would expect that at least to start disappearing. This is like n equals to 4, these 4 things, and they would also get less intense. The higher harmonics would still be there, but that would become less prominent. And so what happens when you actually multiply these things, 2 things together, is you've literally firstly taken out the average value of the image. If you look at this image, its average value is roughly gray, okay? And that's literally because you have subtracted off the F00 keeps the average value. You've subtracted off the average value of the image. And then all the other things that very, very slowly are gone. For example, shadows is the main thing that disappears, right? And this is also one of the main uses when you, especially if you've taken photographs and person's face is in the shade and you don't have the details. If you do cut out the low frequency part, you can sometimes reconstruct that image that was in the low frequency regime. Okay, and so the basic result of this particular filter is it attenuated low frequencies, and what it does, it removes shadows. Okay, it may not necessarily be a better image to your taste, but there are certain features that it highlights and others that it suppresses, and all filters do that. And now the question is, if we've done this, what did we actually throw out? Can we quantify that? Okay, can we sort of look at everything we got rid of to get this image from that other image over there? And the answer is yes. You basically do the same thing, except that you invert the filter, right? Instead of cutting out the low frequency part, let's now see what happens if we just keep the low frequency part and throw everything else away. Okay, and just remember, this is 1/10 of the total frequency space. So what we threw away here is basically this little circle of 1/10. So what we're going to do now is keep like this tiny little bits and throw all the rest away. So let's do that. So here's our image. And so the filter we're going to use now is simply going to be H tilde, which is equals to 1 minus HUV. Okay, so it's literally the previous filter HUV was simply 1 everywhere except in the center. Here we've subtracted that from 1, so we've got it basically 0 everywhere except in this ellipse in the center. And so if we then go and we multiply it with a Fourier transform, all we get is this tiny little core in the middle where the spike was. Okay, and we're throwing everything else away. In other words, we're throwing literally 99% of the Fourier transform away. And if we reconstruct this thing, remember, we do first shift FFT it, then we the complex transform, then we do the inverse, 2-dimensional inverse Fourier transform, then we take the absolute value, and then we rescale it between 0 and 1, say. If we do that, this is the image we get. Okay, so literally you can see in this iris, everywhere where things were sort of shadowy, and like this leaf, and that part over there, and this part over there, you now comes to the fore. You can see that everything varies very slowly because there's a limit on the maximum amount of frequency we can admit in our image. And so in some sense, this thing is the complement of the other filter we had. And what you also know is because Fourier transforms are additive, in other words, the Fourier transform of a function plus another function is the sum of those the Fourier transforms of the functions independently. Okay, you know that this image plus the other image, a linear combination of them will always give you back our original image. Okay, so basically what we've done is this filter keeps the low frequencies, okay, and basically removes the high frequencies. Okay, so just a summary. Let's see the two images together. I couldn't fit them all in, but here is our original image that we had, and this is the image where we threw away all the low frequencies. And so I call that a high pass filter. We throw away all the low frequencies and all the high frequencies were allowed through. Okay, and then this is the image where we put the low pass filter, which was just 1 minus the high pass filter. And here you can see all the shadowy regions came through. And if you combine these two, possibly a rescaled version of them, then you'll get back our original image. Okay. And so it's very, very nice in some sense. You can use the Fourier space to decompose an image into sort of a more detailed version and a more slowly varying version. And where you use this a lot is simply if you're interested in edges. So typically here, the details of where things change are highlighted. Then you tend to put a high pass filter on top. Okay, so what I'm going to do now is take a step back. That was sort of a tour de force in what you can do. And I'm going to look at some of the basic filter properties and sort of the math that we use to describe them. In fact, some of the things that I programmed to actually make those images. So the most basic filter we have is we call it a notch filter. Okay, and it's an extreme case of the filter we had. All you do is you say, fine, our filter HUV is this, like those, so, and all it does, it sets the pixel, the single pixel, at the center of the image to 0, and otherwise it's 1. Okay, and so what this notch filter does, and it's useful sometimes when you are, at least load your image and you do your Fourier transform to actually check this. What this filter does is when you transform it back, it sets your average value of your image to 0. So if your image had values between 0 and say 1, and you apply a notch filter in Fourier space, you will basically have the values of your image, say, be between -0.5 and 0.5. Okay, so on average there, they will be 0. Okay, so the effect basically F sets F00 to 0, making the average of the filtered image 0. And that's a nice way to center your image, and then you can expand it again, that you have the full range of your grayscale of your display. Okay, and now the ultimate goal of at least frequency domain analysis, of which we're just getting a taste, is basically if you could go and you could identify spatial image effects, basically that are caused by specific localized frequency domain components. Okay, and so so far we've seen one where our shadows are slowly varying things are sitting at the center, and the rapidly varying things, the edges are further out. But more than that is possible. In fact, I was hoping to try and remove the stripes of the zebra, but I didn't manage to do it. So I'll actually make you, if I manage it, I'll make you a video just for fun showing you how that's possible. But so what we're going to do is the most basic versions, or understand what's happening with the most basic stuff, and then try more fancy things later on, or on your own if you wanted. Okay, so that's the aim. You have this powerful way of transforming to frequency space. Then you want to go and identify, do certain things in frequency space, because you can see the information's already concentrated near the origin, and that has quite a large impact on what happens. So typically, filters can be split into 2 categories. And we've actually seen those 2 categories already. The one is a low pass filter, and its basic properties: it lets low frequencies pass, it kills high frequencies. And what I must say is I gave you one example. There's a whole series of filters that can be good low pass filters. And in fact, what we're going to do next is discuss how you make a filter that actually is a good low pass filter. So it lets low frequencies pass, it kills high frequencies. It's usually some sort of textbooks call them smoothing filters. They basically tend to blur things. Its feature is it blurs the image, and another place is it removes edges and noise. So sometimes it happens less now. You get static on your image, like a whole bunch of white dots that go all over the image. In fact, the place where I get it a lot actually is I've got a camera that watches the trailer if I ride with animals in the back of the trailer. And the camera couples the car with like a Bluetooth transmission. And whenever I go through a place where the police have radar, I get static on my image that comes through. And that static is like all these white dots that comes from the interference of the radar with my camera. So I know before I'm in range of the radar that it's coming simply by watching the camera on my trailer. So I've got a very good police radar detector inadvertently in my car. But anyway, suppose these dots were to worry me, and I didn't view them as valuable because I now know there's a policeman that's going to catch me for speeding, which I can never do if I'm pulling a trailer, because I usually go at like 60% of the speed limit anyway, but so it's a totally useless thing. But what you could do there is, if you had an image with all those speckles on it, you could pass it through a low pass filter and it would immediately remove all the speckles, and you would actually get a very good image, especially if it's this high frequency oscillations that you get from radio interference. So that's the one category of filters. The second category of filters is what we call high pass. Okay, it tends to let high frequencies through, and it kills off low frequencies. So that's the first example we had, and it's generally a sharpening filter. It highlights edges, and it has the disadvantage of, if you have a noisy image and you do a high pass filter on it, it'll get worse. Okay, so all these filters are not perfect. What happens is, low pass, you lose high frequency, so you lose detail. High pass, you emphasize noise, so you actually might be amplifying things you don't want. But it's a different way of looking at the image. Okay, so it will emphasize edges and abrupt changes in the image. So typically, if you're looking for breaks and stuff in people's bones or stuff like that, you'll put a high pass filter on it, because it'll make those things off. It'll make fine hairline fractures and stuff stand out. And a lot of the processing software that actually looks at these images have this type of thing built in, and you can actually change the threshold of the high pass filter, and it is a way of looking for sort of features that you find interesting. Okay, so what I'm going to do now is I'm going to look mainly at the no pass filters, mainly because more often than not they come in pairs. In other words, if you have normalized your low pass filter that its values lies between 0 and 1, then you can make a high pass filter simply by saying 1 minus the low pass filter, or inverse. If you have a high pass filter like we did in the first example, and you say 1 minus the high pass filter, then you actually have a low pass filter. They are in some sense complements of each other. And what I can also say is, here in this course we're just going to treat them as independent things, a filter that you apply once. What people have done, and where one of the ways that they actually derive wavelets, is you have a whole stack of them. In other words, you send the image through a low pass and a high pass filter, you get two images as a result, and then you send that output again against the low pass and the high pass filter, and you make a whole cascade of them, and those things have other properties that are very, very nice. but they all come back to having low and high pulse filters, the basic properties of them. Okay, and so what I want to look now is basically look at some of the designs of these filters. Okay, so basically the smoothing filter is a low pass filter effectively. It's basically, I started getting tired of saying attenuates. It's basically designed to kill off the high frequency components of your Fourier space. And the toy model, or sort of an example that I start with, that most people, and the most naive thing to start with, is what they call an ideal low pass filter. Okay, and what that filter does, it literally does what we did in the thing. In the first example, it simply is HUV is equals to 1 if the distance, if DUV is less than or equals to 0, and 0 if DUV is greater than 0. Okay, so roughly what I've said here, and I'll define these things now, is I've got this image like here, where I'm 0 all the way out here, and I am 1 all the way inside there. Okay, so D0 is basically a specific distance from the origin of the transform. So in this image, I've shifted my FFT already. So here's the origin, okay? And so D0 is a specific distance from there. It's rough. In this particular example, it's the radius of the white circle, and it's called the cutoff frequency, okay? And you'll see that this feature actually generalizes even if we change the filter. Okay, and here over there we have the DUV. It's actually the distance from the point UV to the origin. In other words, suppose you were to have a point over here, and I would say its coordinates is, say, u equals to 3, v equals to 4, then DUV would be the square root of 3 squared plus 4 squared. You would just use Pythagoras. Okay, when your images aren't square, you can change that a little bit and rescale it. That's what I did, why I got an ellipse onto my other image, because it's typically, you tend to rescale the image so that the sides are square before you do these things. So this is what the distance is. So the basic filter design is if DVU, the distance from the origin, is less than 1 or less than D0, then it's 1, otherwise it's 0. Okay, so, and all it does when you multiply it, it's kind of obvious given the example I've given. All frequencies outside the radius of DU0 are basically, inside the radius remain unchanged, and those outside are attenuated and set to 0, and you then do the inverse transform and get the image. Okay, so typically when we have like these software programs that enhance your face or get your, or the ones that look at the medical images or the x-rays or stuff, you'll have a bunch of options that say apply low pass filter, apply high pass filter, and you'll click on it and it'll do something. Okay. In this usually what it does is it hides. It actually guesses a D0. Okay. And the problem with choosing the D0 is that suppose you had one image and you sampled it in a specific way. So say you had one image out of, say, 500 by 500 pixels. Okay, you did the Fourier transform, you would get a Fourier transform that looked a certain way. And then you had a second sampling of the same image. So your first image was, say, 500 by 500 pixels. You take the same picture and you have 250 by 250 pixels. Okay. So it's just the core sample version of your original image. What you would like, if you do the filter on it and you choose a threshold, that the result is the same. But clearly it's not going to be, because the Fourier transform of the big image, like the 500 by 500, is going to have 5 by 500 dots in, and if you choose a D0 there, you're going to cut out a different amount of frequency space from the smaller image, which is just going to have half the number of pixels. So this D0 is not a good number to choose. It turns out what is a better number to choose that allows you not only to account for the different sizes in images, but also the different possible ways in which images changes. For example, you could have a really boring image with a person like in the front over here, and you could have another image where you've zoomed in on the person. And the thing that's important for you is the person. If you choose a certain threshold in this way, then you are going to get vastly different results. And what you would like is always to be, say, focusing on the changing of the person. So, and by no means a foolproof way to choose D0 is to do the following thing. So what you do is you say, let me look at the power of my image. So the way we define the power of an image is simply to take every single pixel of, in this case, the Fourier transform, and square it and add it together. Okay? And it actually turns out that the power of the image in Fourier space and the power of the image in real space is actually the same. Okay, so what you do is basically you take your image values, you square them at every single point, and then you add them together and you get the total power of your image. And then what you're going to do is you can ask a question. You can say, what fraction of this power do I actually keep if I multiply it with a filter? Okay, so then I can say a second question, for example, the full power of my image is every single pixel squared, and I'm going to define PR to be the sum of the pixels squared that are kept, but I add only those pixels that lie inside the circle. Okay, so obviously when R is 0, I keep none of them. When R is small, I keep just a small number. And as R gets bigger and bigger, I keep more and more. So this PR is an increasing function of R. Okay, and then what I can do is I can say, let me look at the percentage. In other words, the ratio of 100 times the fraction of PR over PT. And then I can choose that. I can choose my R so that this percentage has a certain value. And if you make your choice for R that way, you will get different R's for different scaled images, as well as different R's for different types of images. But the behavior it has, at least visually, will be close to the same. Okay, so basically it's better to examine this alpha, which is to use that as a parameter, which is the ratio of the power kept by the filter divided by the total original power of the image, and that then is used to choose a threshold for D0. So what you basically do is you choose alpha and you increase D0 until this fraction is what you want it to be, and you do that for every single image you want to look at in this particular case. And so typically in the programs that do high pass filters, they've do low pass filters, they've chosen alpha to lie somewhere between 1 and 10%, and then you can actually have the same effect on every single image regardless of the nature of the image. And so that's usually the first guess, and then if you have an operator, you allow them to fine-tune how much of the high and low pass filters you're actually keeping. And I'll once again put up my codes that did the two filterings, that you can actually go and you can play with it yourself and see if I change the size of, say, the circle, what is going to be the low pass filtered image and what am I going to have in the high pass filtered image, because you can literally use this to partition your image into two parts, and you can do it in a way that you learn the most without losing any information. Okay, so choosing it this way is the advantage that you can apply consistently for different images. So, what are the advantages of this ideal low-pass filter? The one is, well, it's easy. It's simple to implement. You put this you keep everything inside a certain radius. You throw the rest away. Two is it's intuitively easy. You know exactly what you're doing in Fourier space, but do you really know what you're doing in physical space? Okay. So the disadvantage of this filter, which is why it's not used, I used it for the example, but very often when you're doing, looking at medical images, you don't use this because you can get artifacts from this thing that are pesky. And so what we're going to do is basically explore some of those. So the problems with the ideal low-pass filter is as follows. There are ringing effects. It makes artifacts in your image, and I'll explain to you where these come from. And these are very, very important because if for some reason you choose this filter, and they're always available on the image processing software, you can make effects that can look like a fracture where there actually is none. Okay, so this is why you guys come and study this, is so that you don't go diagnosing mistakes. Or the other place where you can get a lot of mistakes is if you look at brain tissue, they're being able to see the definition of your actual, with an MRI, of the actual brain tissue is one of the way they diagnose Alzheimer's. Right, when the brain starts decaying, and my dad had it, so I know, unfortunately, when the brain starts shrinking, you can see certain lines in your image. And if you put the wrong filter on, you can actually, and you don't know what you're doing, you can actually mimic those lines. And you can give a family a heart attack, or you cannot diagnose the thing early, which basically means the guy gets sick unnecessarily. So it's very, very important to understand these type of things, or to understand the possibility that these things exist. Okay, so the problem with ideal low-pass filters are that you get ringing effects. Okay, and what this does, it not only gives you false features, but it causes unnecessary blurring. And so what I want to do is explain where they come from. Okay, so the origin is Gibbs phenomena. So if you remember what Gibbs phenomena was, is if you just in one dimension take a Fourier transform of something that's discontinuous, you have this overshoot and wiggle just at the discontinuities. And so this actually happens with the ideal low-pass filter. Okay, so let us have a look at an example. So here's just another way actually of writing the ideal low-pass filter. We have some function f of xy, which is equals to 1 if x squared plus y squared is less than or 0 equal to d0 and 0 otherwise. Okay, and so if you draw a radial, let's suppose you draw the radial profile of that function. Can you just put it on the board? Suppose you have an ideal low-pass filter and you take a cut through it. Okay, and you from your origin you start at 0 at 1. Just draw what's it? F versus R. If you sorry. We're going to go for neon pink. Maybe not. Okay, so just draw F versus R. R on the x-axis. Okay. And then what you have is basically 1 and choose d0 equals to 1. So you basically have one little box here. Yeah, but straight down. Okay, and then across. Okay, so that's basically what this thing is, but in R, right? And what it is, you've rotated it around the axis, so it's your little disk. And so what you have as you go out is you have this jump discontinuity. When R is equals to D0, you go straight down. Okay, so the thing is discontinuous there in 2 dimensions. And so what we want to do is compute the Fourier transform of this thing. And you have an example, the last example you have in the problem set that's due tomorrow is a similar kind of problem, except that you don't just have a disk, you had an annulus. Okay? And the good news is when I actually tried to do this one, I realized that one is doable, but a little bit harder than I intended. So that one has now become a bonus problem. So if you want to do it, it's fine, you'll get credit for it, but I will mark the problem set out of whatever it is besides that one.
So it's only question 1 and 2?
No, question, just the last, I'll speak to, just the one that has the annulus. So not even the whole question you lose, you just lose part B of the final one. Okay, but I want to do, it's such an important problem, which is the reason I put it in, and you can actually do it, that I actually just want to tell you how you would have started doing it. So I do encourage you to still try it, even if you don't integrate it numerically, do it with a computer, that you get a feel for what it was. There was a very good reason why I wanted to put it in. So the way you would do this problem, suppose you were given the question just like in the homework is compute the continuous Fourier transform of this thing. Okay, the way you would do it is, because the only variable you have here is r, in other words, it's spherically symmetric, what you would do is you would go to polar coordinates. Okay, so I'm basically going to do it for you. So remember, the polar coordinates was you, in the Fourier space, was you had something that looked like the radius cos phi v omega sine phi. And then we had our x coordinates in polar coordinates as well. Okay, and then in lecture 7, I went on and I rewrote the Fourier transform in terms of the polar coordinates. So what I did then is I basically proved, and this you must know how to do, how the Fourier transform goes from your x and y coordinates into your polar coordinates. And that the integral then takes place from 0 to 2 pi, the integral from 0 to infinity, f of r and theta times r d phi. So this r here is important because it's your Jacobian. Okay, so these are the steps that you would do in solving the problem, okay, and including that last problem that I gave you. So you write it as polar coordinates. Then what you want to do is you want to change this function into a polar function, okay? And the way to change it is easy. It is simply a function that does not depend on theta, but it is 1 if r is less than d0, okay? And so what that does is very similar to when we were doing the convolution with the boxes. What that does is basically f is equals to 1 as long as r lies between 0 and d0. So you can then take this integral and write it like this. Okay, so it's literally the integral from 0 to 2 pi, the integral from 0 to d0 of this whole thing. And then the next step, if you want to compute the integral, is look at this thing, okay? You can do two things. You can either try and compute the theta integral first, which is seriously nasty, okay? Or you can go as far as you can, and you can compute the integral of r first. And that one you can actually do because you've done it already. Right, so if you group everything except for r, in other words, 2 pi times omega times cos of phi minus theta, and you call it something like, call it beta, then you have an integral you already have. Then you basically have r times e to the beta I r, which you can already do. Okay, so the next step would be you do that integral, you put in, which you did a lot of in the previous tutorial, you put in the boundaries which are constants, you get an answer, and then you are left with an integral over theta. Okay, and that integral that you're left with is the nasty one. Okay, and so that's what makes the problem a bonus question. Is you go through the steps as far as you can, and then when you get to that last integral, it can actually be done. So there are people that have studied these things a lot, and the way to go look up is basically, I'm going to leave the image here, is you can the integral that comes out once you've done the R integral, you can actually write as a Bessel integral. Okay, so if you don't want to do that, that's fine, but another way of exploring is simply to do it for me numerically. Okay, so it's a bonus question. You don't have to do it because it is harder than I intended it to be. It's a very important thing to build your intuition with. Okay, so I encourage you still to go and play with it. If you've worked on it, you won't lose anything by what you've done. It's just, I don't think it's fair to actually mark you out of it for it. Okay.
Can you find such questions in the test?
Like this one? No. It's usually not. If there is, then I would. Sometimes in the test I add extra stuff that are bonus questions, and those are harder. But like the test, it will be are designed to be able to do in 2 hours. Okay. So if I were actually to give you the answer to the integral, then maybe, but usually not. Okay. What you will get in the test is know how this derivation works. Okay, know how the integrals work. So those type of questions I do ask. I also do ask a lot of applications like the problem sets you've had. In fact, the problem sets you've had, the reason why there's so many problems is that you can have practice problems as well. So the problem set, but I'll talk about that once I've done with the lecture. Okay, so you can write it out analytically as a Bessel function. What you can also do is just play with it numerically. In other words, take a little circle like that, work out the discrete Fourier transform and zoom in on it. And if you do that, you'll see you get something that looks like this. Remember when we did the Fourier transform of a box, just a box in one dimension, we got the sinc function that did that. Okay, this is the two-dimensional version of that. It's not exactly the same, but what happens is if you do the Fourier transform of that box, you're going to get a central cone like this, and then it's going to look like a sombrero Mexican hat with a wobble. So you're going to have your central cone, it's going to come down, and then it's going to wobble like that, and then fade away. So if you look at it in grayscale, you see here is your central cone, but around it are these rings, ever increasing rings that fall away with intensity. Okay, and these rings are the Gibbs phenomena or the ringing because you have that discontinuity in your two-dimensional space. And so the problem is the inverse Fourier transform of your ideal low pass filter always has these rings. And if you think about it now, when you multiply something in Fourier space, you actually are convolving it in real space. So imagine if your original image was simply two dots. Okay? If you were to apply the low pass filter, what you then would get is two dots with these rings around them. Okay? And what that does is if you have an edge, those things add together. Okay, and what's going to happen is I'm actually going to draw it for you. Or maybe, yeah, I'm actually going to draw it for you right now. The people that are listening to the talk will just have to wait. Okay, so let's have a look. Suppose you have your image, and your image has an edge that looks like that. Okay, it's a sharp edge. You take it to your Fourier domain, you basically multiply it with your ideal low pass filter, and you bring it back. And so what you have is effectively that every single point over here is now going to be convolved with that big bump with little circles around it. So over here, instead of having a sharp edge, you're going to have a point like that. And then say, and you're going to go on, and every single point, you're going to have a thing, and it's going to be replaced with something like that. Okay, and so what's going to happen is over here, those are going to disappear. They're going to, the wobbles are going to cancel out. But your image is actually going to, once you've added the low pass filter, it's going to be something like that, sort of blurry. But then you're going to have the secondary feature that's going to come in, because over here, like where all those you always see, right? So you're going to have this little dwarf line that comes in here, and another one that's going to come along there. Okay, low in intensity, but sometimes it makes it look like there's a shadow or a ring around sharp features if you've applied this ideal low pass filter. And that is a dangerous thing. That has been mistaken for proper features. Okay, so that's the problem with ideal low pass filter, right? Because it has this discontinuity in Fourier space. When you take the inverse transform, you're adding this thing, and you can add, you actually in some images you can see these rings coming out. What's the solution to that? Because a low pass filter is useful, right? We want to smooth things. We just don't want to smooth it in a way that gets extra little rings in our image. To get rid of this unnecessary structure, basically the solution is we must find a continuous filter. We must find a filter that doesn't have that sharp jump. And even though it's more complicated, the moment you do that, you no longer have this Gibbs phenomena, and your solution converges faster. Okay, very, very important concept. I can't emphasize understanding the mistakes of this ideal low pass filter enough. Okay, so let's have a look at an example of such a filter. Okay, so they call it the Butterworth Low Pass Filter. And what that is, it's simply, we say our filter is H of U V0 equals to 1 over this thing. Okay, so once again here, we're going to have an integer that we call n, which they call the order of the filter. Okay, and what's interesting, if n goes to infinity, then this thing basically becomes, a high pass filter again. Sorry, a low pass. It becomes the ideal low pass filter. So this is the order of the filter. Okay, D0 once again is what we call the cutoff distance. And du0 is once again the distance from the point to the origin of the transform. So once again, it's a filter that's dependent on the distance from wherever you are to the origin of the pass transform. Okay, so once again, it's a filter that's a function just of the radius and not of the angular dependence. And the thing to observe here, we have this D0, which we called up here with a cutoff frequency, but the reality at D0, this filter is not 0. Okay, so at D0, when D is equals to Z0, basically this filter has got half its value, so it's decreased by 50%. Okay, and in this particular case, we call that the cutoff. And basically it's decreased by 50% from its maximum value, and that gives our definition of the D0. Why is this D0 the same as the other D0 that we had, which we also called the cutoff frequency? And once again, I'm going to put an image on the board, and this is actually, I think, the end of my slide, so I'm going to stop the video. But let me just explain